Hello, welcome back to another exciting episode in chemistry. I'm Dr. Bettina Heinz, and we'll teach you something interesting information that relates to heat and energy, which is also called thermochemistry for our purposes, the chemistry of thermal changes, interactions, etc. These are the topics we will go over today in this episode. Energy, especially kinetic and potential energy. Basically, all energy can be reverted back to the energy of position or stored energy and the energy of action or motion, meaning energy in action that is able to do work. Then the difference between the two fields of science, thermochemistry and thermodynamics, and heat versus temperature. Some people might not understand what's the difference between heat and temperature. Then enthalpy, which is the actual symbol H, because heat, in the physical sense, is usually symbolized by the letter Q. And the units involved, exothermic and endothermic changes. That means heat given off to the environment or heat absorbed from the environment. If it's only energy, we call that exergonic and endergonic. But that deals more with the field of thermodynamics, which we won't cover. We will cover thermochemistry. Then we will talk about the conservation law of energy or heat. So for our purposes, it is for any heat exchange, the heat lost will be the heat gained, or the sum of all heats will always equal 0. Then we will learn about the capacity of a body of matter to absorb heat, more or less, depending on its internal structure. The specific heat capacity, or specific heat for short, molar heat capacity, and the Dulong-Petit rule, or law sometimes, as it's called, and calorimetry and calorimeters, which are the devices for measuring heat exchanges. Now energy, if we go and look at our first view graph, we can see that kinetic and potential energy are related at all times. So when kinetic energy is at its maximum, like here at the lowest point of the swing that oscillates back and forth, then the kinetic energy will be the highest once the swing passes here the lowest point. The potential energy, or energy of position, is the highest at the turning points. That's where kinetic energy is 0, because the swing is temporarily at a standstill. So no kinetics are involved. And here, the potential energy has its lowest position. Therefore, potential energy is 0, where kinetic energy is at its maximum, and vice versa. When the potential energy is at its maximum, the kinetic energy is at its minimum. So thermochemistry relates to heat exchanges. It tells us that bodies can absorb more or less heat, and the exchanges are a result of this phenomenon. So thermochemistry mainly deals with thermal phenomena of chemical subjects. The general formula is, as we see here in our example with a coffee cup, if I put a spoon into my tea or coffee, the spoon will absorb some of the energy of the hot coffee and will cool it down, depending on what type of spoon I use. I will illustrate that a little bit more in detail as we go along, so we're not going to pay any attention right now to this calculation, but we can certainly use this important equation that any change of heat And here we must speak more of what we call enthalpy. I'll get into that in a moment. H stands not actually for heat, but for enthalpy, which is a heat change at constant pressure. That means pressure is not changed. So the change of enthalpy is mass of the body of matter times small c with a subscript p, which we refer to as being the specific heat capacity, which is a material constant, a material property, and it's always the same for a certain chemical. And delta T means the change in temperature. So we can only measure the changes of heat in temperature and when we know the mass and the specific heat. Now, if the heat is smaller than 0, then the heat has a negative value, and that means the heat is given off to the environment. If the heat is positive, or larger than 0, a positive value, then that means the heat is absorbed away from the environment. So we always look at our system in relation to the environment. In order to quickly tell you what the difference is between thermochemistry and thermodynamics, we will look at these concepts quickly. So thermochemistry is practically observing the phenomena and doing some simple calculations with these heat exchanges. And thermodynamics is a whole field in itself that involves an intricate study of the exchanges of internal energy, which is chemically stored energy, with more observable types of energy like photo energy, electrical energy, etc., etc. So that is a much more intricate subject matter that is beyond our scope right here. Thermodynamics, which also deals with the first, second law, third law of thermodynamics, etc. Now, just to show you quickly, I'll get back to that later, how chemical energy can be converted into other forms of energy, like electrical energy of the eel here, or the anglerfish in the dark, in the extreme depths of the oceans, which is completely dark. The animals have to make their own little lanterns, so they convert chemical energy into photo energy. The firefly does it also, but the firefly doesn't really need it for visualization purposes, but it uses it for signaling to other fireflies, like a flashlight going off and on, much faster than we can actually see. Plants, of course, we all know that plants convert light into chemical energy, which is stored energy or potential energy, you could say. Animals convert that to mechanical energy, to the kinetic form of mechanical energy. So you see, energy is constantly being exchanged in its varieties, in its forms, in representations or manifestations. And that's very interesting chemistry to study, but that would go too far in our course right now, but I'd like to cue your interests. We now come to what we consider thermochemistry for our studies. Thermal energy and chemical reactions lead to heat exchanges between substances. So when a chemical reaction takes place, heat can be given off or absorbed. But it doesn't have to necessarily deal with a chemical reaction. It can just be that a hot substance transfers its heat to a colder substance with which it comes in contact. Here's a very nice representation of a reaction that produces heat or absorbs heat. That is not so common. Most reactions are exothermic. That means they give off heat, especially combustion reactions, etc. Here's a reaction which is utilized for cold packs. So if you have a sprained ankle or something like that, and you want some soothing coldness, then you can take these chemicals, barium hydroxide octahydrate and ammonium nitrate. These are two dry chemicals, and when they come in contact with each other, then they liquefy in each other because of the reaction products, because they produce water. They also give off ammonia gas, which might be helpful if you have a cold at the same time, and barium nitrate, which is dissolved in the water that is being produced. So here's the person who has an accident on the sports field, and a cold pack is applied to his knee. That means the energy per mole is 170.4 kilojoules are absorbed per mole substance reacted. So that means where does the heat come from that it needs for this reaction, to drive this reaction? It comes from the knee of the individual. And the person will then feel it as a cold sensation. So here we can see roughly how this happens. We have a test tube. We can put two chemicals together, A and B. And the thermometer is at 25 degrees, which is usually considered room temperature. And then when the heat is applied from the hot leg, or remember, body temperature is hotter than the environment, right? So once the energy is supplied, these chemicals react, and we get barium nitrate, water, and some ammonia vapors. And the resulting temperature is minus 20 degrees. So that's 45 degrees drop in temperature from room temperature to the final temperature. And you see the heat exchange was from the leg into the chemical reaction that was then driven to its completion. And this chemical reaction is utilized in the form of a cold pack. That means on one side you have the one chemical in crystalline form, of course, and the other side the other chemical in crystalline form. And when you break the barrier, then the chemicals become in contact, and you have that desired effect of cooling. Now, every chemical is different. Every chemical has a different structure, different molecular makeup, atomic makeup, different intermolecular forces involved. Gases are different from liquids. Liquids are different from solids. Solids are different according to their crystal lattice structures, etc. So every chemical has its own, what we call, heat capacity. So heat capacity means how much heat can you absorb until your temperature is raised by 1 degree. That is how heat capacity is defined. It's not based on any particular amount. It just means how many joules, how many energy units can you absorb to raise your temperature by 1 degree. And it's, of course, the degree centigrade or the degree Kelvin, which have the same interval. So it doesn't matter whether you use centigrade or Kelvin in this case. The old heat unit, remember, was the calorie that we still use when we want to know how many calories we're eating for dinner tonight. And specific heat is directly related to the heat capacity, only now it's based on a specific mass unit, and that is the gram. So specific heat is joules per degree Kelvin, we don't write the degree sign, per gram, or joules per degree centigrade per gram, whatever you might want. Remember, Q is the actual symbol for heat. We usually use H when we deal with enthalpy, which is heat at constant pressure. So the ability of a body of matter to absorb heat depends on its internal structure. Has to do with kinetic energy again, because when heat, remember, heat is a form of thermal energy, which is related, according to the kinetic molecular theory, to particle movement. So the amount of thermal energy that can be absorbed by a substance depends on how many degrees of freedom it has internally for particle motion. See? So aluminum is by far one of the most heat-absorbing substances, has a low density and a high heat capacity. It's 0.9 joules per degree Kelvin per gram. Silver is 0.236. Gold is very low. It's 0.128. It's a very dense metal. It's 19 grams per milliliter and has a very, very low heat capacity. You can see there's some kind of inverse relationship between heat capacity and density. So other people observe that too, not only you. And we will learn about the relationship later on. It's expressed in the Dulong-Petit rule. Water is has a very high heat capacity, 4.18. Benzene, an organic solvent, is 1.74. Ethanol for drinking is 2.45. Carbon is 0.716. Pretty high. We wouldn't expect that. Copper is 0.386. Sulfur is 0.736. And of course, there are many, many other values that we can find for other chemicals as well. So when we want to look at how much coffee can absorb when a cold spoon comes in, or let's say how much heat can be transferred from the hot coffee when a cold spoon comes in, is interesting to know. And I have a few models here that can illustrate how these things are related. So I'm going to put my little surface down, my background. And these little guys, they're foam packaging things. And they can illustrate very nicely a crystal lattice structure. And here is my heat source, my Bunsen burner, for instance. And if the particles are packed tightly together, they don't have that much freedom to move around. So therefore, their heat capacity might be low. So high density, low absorption power for heat. If they're a little bit more spread apart, the lattice points, or the individual building blocks of the crystal, of our solid in this case, then we have more degrees of freedom to move around. So the energy can be better absorbed. Now, to illustrate what the difference is between temperature and heat, let's look at the following. We have here our heat source. Let's say that's our Bunsen burner. And we have 100 grams of a certain amount of material. So how much heat can it absorb for its temperature to be raised by 1 degree? We all know that it takes a certain amount of heat. Now, if we take 200 grams of the same material, then you can all figure out that in order to raise the temperature by another degree, by the same amount, you need more heat because we have more mass to heat up. So you see, heat and temperature is quite something apart. So heat is actually a quantity that is absorbed by matter, and the thermometer measures the heat change of the material. So if we have twice the mass, the heat has to be spread out within the material, so you need more heat to reach that same temperature rise as you do for using only a smaller amount. So I hope this makes sense. Now, another little gadget that I have prepared for you is a nice cup of tea. It's very hot. And let's say you're invited to the White House or to some nobility, whatever your choice may be. So we have here our teacup, and we want to linger, we want to stay a long time. We don't want the tea to cool off so fast. So what spoon would I use to stir the sugar in my coffee if I prefer sugar? Would I use a gold spoon, an aluminum spoon, or silver spoon? Now, aluminum has a high heat capacity. We remembered. So if I put that in here and stir my coffee or tea, whatever you have asked for, this looks more like a, well, sort of in between a coffee and tea cup. The aluminum will take all the heat out. So your beverage will cool down fast. And then you have to leave already, or you have to ask for a second cup of tea. Now, if you use a gold spoon, the gold, remember, cannot absorb much, had a very low heat capacity. So I think for noble purposes, it's better to use the gold spoon. The silver is sort of in between, right? So we could use a silver spoon. Silver appears also to disinfect, so that has an added attraction. By the same token, we can ask ourselves, how specific heat can make certain decisions for us of whether I should use a copper pan in the mornings to fry my eggs, or whether I should use a aluminum pan skillet or an iron skillet to fry my eggs. Now the question arises, if I have not much time in the morning, what pan would I choose? If I want to make a beautiful meal that needs to transfer the heat slowly but in a long fashion, I would choose accordingly. So if I want to do it fast, would I use the aluminum pan? Or would I use the copper pan? Or the iron skillet? So you could say the aluminum has a high heat capacity, so it absorbs a lot of heat. Does it transfer the heat as well, fast, quickly to the eggs? That's the question. If it takes all the heat, then it also transfers it to the eggs, hopefully. So you see the specific heat plays a role of how quickly heat can be transferred, how well it can be transferred. Some material doesn't transfer heat at all, like a styrofoam cup, right? This is an insulator. This material does not absorb heat, has a very, very low heat capacity, therefore it can be used as an insulating material. In chemistry, we can even utilize that as a little calorimeter, in which we can do measurements of heat transfer without heat getting lost to the environment. Now we are getting to the law I talked to you about, and that's the law of Dulong-Petit, two French people, who noticed that the molar heat capacity, and you know molar heat capacity is just like the gram heat capacity, only it's joules per degree per mole substance being heated and not per gram. So they noticed that the heat capacity, or the specific heat capacity of a substance, is roughly inversely proportional to its atomic weight, and also the volumetric heat capacity, or thermal capacitance, that we can also say, is constant for all solids. So the thermal capacitance, or the thermal volumetric heat capacity, is volume times density times specific heat. But in the end, for all crystals that deal with lattice vibrations, we can say that the specific heat capacity of a crystal is inversely proportional to its molar mass. 3R means here, as we know from the gas laws, that R is the universal gas constant. We are not using the value that we were using for the gas laws. We're using another value here that relates joules per Kelvin per mole, not liters atmospheres, but joules. So we get another value, and it's roughly, when we calculate it out, we can say that 3R is 25 joules per moles per Kelvin. So that's called the molar heat capacity. Most solids come up with this number. It is relatively a constant value, but you can't completely go by it because there's some variance. So some are less than 25, some are more. But usually solids, including the metals, which have a metal lattice, will have 25 joules per moles per Kelvin. So we can use this relationship to calculate the molar mass of an unknown substance. Once you know the specific heat and you know 3R, then you can calculate for the molar mass. Or if you know the molar mass, and then you can easily calculate the estimated specific heat capacity. Calorimetry is the measurement of heat exchanges, and we use a calorimeter, and I already pointed out to you in simple lab experiments, we use a very cheap one. This is our coffee cup that retains the heat. And if it gets too hot, remember you can use a cold spoon to absorb some of the heat. By the way, when people make jams or heat some fruit in order to make some dessert, then once you get it from your pot, from the stove, from the skillet, you can pour it into your glass jar with a screw top. But there is a danger of the glass cracking. So what old housewives usually do is take a spoon, and an aluminum spoon would be the best, put it in the jar, and then pour the hot liquid or mush or whatever you may call it, the sauce, into the glass. And then the spoon will absorb any excess heat and the glass will remain intact, and you can have some wonderful breakfast. I will show you here some equipment that we use before we come to a stop today. How would I measure or determine the specific heat of these little nickel granules? So that would be the nickel, element nickel. So I can put them in a test tube, to be careful not to break it. Heat it up in a hot water bath. Now that water bath is just a beaker filled with water heated over the Bunsen burner. And the metal will then have the same temperature as the hot water bath. It probably might be 100 degrees or 98 degrees. I record the temperature, I record the mass of the nickel, and then I pour it into a calorimeter that has some cool water, so I know the mass of the water I have in here. The specific heat of water is 4.18 joules per degree centigrade, per gram, excuse me. And then I pour into the water my heated metal, and then I measure the temperature again, and then heat gain equals heat loss, so we have a medium temperature, and then I can do some nice calculations, and this calculation I will show you in our next episode, and that will be the source for calculating the specific heat of this nickel material. I know the mass of water, I know the specific heat of water, I know the temperature change, final minus initial, and the mass of the metal, etc., and then I can calculate. Well, see you